is low level because we don't manipulate, except for the cutting, but we put together the different data. So our starting data is just the raw data put together, and this is what we call low level. In middle level, we do something. We extract a feature from our data. So for instance, we take juice, and in this case we extract feature because apple juice is not the same as an apple. Or we do candies of the fruit and put them together in a cake. So in this case, we extract features and then we mix them. And we call this mid-level data fusion. Because in this case, we do not merge the raw data, but we merge something that we have extracted from the raw data, and we call this something in general features. Then there is the high level, and in this case, we do much more manipulation on our raw data, because what we usually do is that we analyze our data first. So in this example, for instance, we assess the sugar, vitamin content, water content of each fruit, and then we merge this information. With the data, usually what we do maybe classification with the first data set, classification with the second data set, classification with the third data set, and they classify sample, not always with the same decision, and we merge this decision together. Or another example, prediction. We do a regression model because we want to estimate the Brix content of wine with one method. Then we do estimate the Brix of the same wine with a different method, and with the third one. And we may have different value of Brix, and we want to merge this decision. Or another very different example, all of us, we bet in who is the winner of the next Football World Championships. So each one of us build up his own model to make this prediction, and we won't match this prediction because we want to go to a bet place, and we hope to have money because we hope to have the nicest decision. So this we call high-level data fusion. In high-level data fusion, we merge decision taken by different models. So in this case, imagine that we do very different things, because we build model, we have an answer for each distinct model, and then we want to match this answer in a sensible way. And in a more formal way, low-level data fusion, we have single block, and we say that we obtain a concatenated or augmented data set. So we just put the different block close, and in this case the shared mode of the sample, but we can do also the opposite. I will show some playing with this. And if we have the block that are all bidimensional, we have this situation, and we can use our standard bilinear methodology, but we may also have data that have higher dimension. So imagine, for instance, gas chromatography, mass spectrometer, we have 2 dimensions, and maybe we have a near-infrared spectra, just 1 dimension, and the same sample. So also in this case, we can do low-level data fusion, and we will mention some way, and in this case, we call it join coupled data, and the methods are a bit more complicated. when we do mid-level data fusion, the situation is easier if I have data of different dimension because I extract features. So imagine that here I do, for instance, a principal component analysis. Then I have the score if my shared mode is the sample. So in this case, I have the score from the PCA from the spectra. In this case, I can have something that I don't know if it is familiar by you, but I can have a decomposition similar to PCA of this data, and I can also have something which are exactly the same meaning of the score. So I can, in this case, instead of component, we speak about factor, so we say we factorize this block, and so we have the analogous of the principal component for this situation. And maybe here, instead of taking principal component, I do variable selection. So I only maybe pick up, I don't know, peak area or a small region of my signal, and I have features. So there are several ways I can extract features. And at that point, once I have extracted the feature, I am in this situation. So this was more complex, I extract feature, I come back to a simpler situation. Of course, when I extract features, I lose something, or better, not lose, but I hide something, because if I analyze this data as such, if I have spectra, here I have the spectral profile, and I preserve the spectral profile. So when I'm going to see my result, in my model, I have some nice plot that tell me which part of the spectral region is contributing to the model, and I can directly interpret, as I interpret the raw data. In this case, my variable are principal component 1, principal component 2, principal component 3. It's not the near-infrared spectra. So I sort of lose this information when I do this extraction. Then I can find some way to come back, because if I see that in my final analysis the second component is very important, I can go back and look at the loading plot of the second principal component and have an idea what was the spectral region that was important there. But I need some post-processing, okay? When I do high-level data fusion, in this case, I take decision for this sample. So I have a feature, monodimensional is the decision for each one of the sample by this analysis of this data, analysis of this, analysis of this. And in this case, I can have high-level data fusion by using the same methodology. So, case of prediction, I can always use partially square regression for doing prediction, but I can use different methods. So I can use partially square regression for data block, and for another data block I can use neural network, or even I can have always the same block. So in this case I can have only one. So imagine I have only this data block. So what I want to fusion is very different method from which I take prediction, and I want to fuse this prediction, and maybe I have only one data block. This is somehow, let's say, one extreme of the high level, because in this case I don't have different data that I want to integrate, it's only different decision on the same data. And then I can have all the situation in between. I can have different blocks with different techniques, all analyzed with a single method. So I merge decision on different data taken with a single method, but I can also have a different method on the same block with different block, and I want to match decision of different method, different data. And this the high level context. In this case, of course, I lose everything of my original data in terms of where this decision comes from. So, for instance, you see less application in chemometrics of high-level data fusion with respect to, for instance, a robotic community. Because you imagine that when you have to do an answer decision, in this case, you really don't care about the rest, and you want to have to merge as many predictions as possible or as many classifications as possible to achieve the best model. And you don't care why you arrive at that point. You only care that you are successful in your prediction or in your classification. So you find much more of this in the engineering community or stuff like that. Imagine automatic face recognition. You don't really care how you arrive. If you recognize that Cos'è is Cos'è and no one else, you are happy if a machine can do this. Which, by the way, is very easy for us, it's very difficult for a machine. That's what is very easy for us human, that even recognize twin people, is very, very difficult for the machine for some reason. Okay, so keep this in mind, because this is a general framework, so when you... Yes?
I am wondering about low-level data fusion. How do you manage the variability between experiments? Imagine that you are fusing two experiments that you try to measure the same, but different days. You can manage the variability intrinsic in the experiment, or maybe you only fuse the data?
Okay, this is a difficult question.
Yeah.
Because most of the time you don't care, in the sense that you assume that even if in the different block the noise level or the error level is different. If you use multivariate data analysis, then somehow you will be able to model this without destroying completely. But on the other side, there are methodology, and most of these are quite complicated. I also have difficulty in understanding, because they are based on Bayesian statistics that try to take care of the different variability that you have in each data. The simplest way to do this, for instance, in the principal component analysis context, is to use, instead of PCA, maximum likelihood PCA. That is a methodology that uses the error covariance matrix, basically, to weight your data before doing the decomposition. So if you imagine to do this for the different block as a sort of, not prior transformation, but changing the modeling, then you can take care of this. Or you can imagine that can be a quick and dirty way. That is usually more my attitude, because I'm not so mathematical as a background. You may think of weighting differently the block. If you know that one block is more, let's say, is less uncertain, it's more uncertain because you have lower reproducibility, higher error, and so on. So you may think to downweight somehow this data. That's also another possibility, which is, and then there are the more sophisticated methods that try really to handle with Bayesian statistics this problematic.
Okay, thanks.
May I also have a question? So low level for me is quite straightforward, connecting some or extending a vector and then doing the same procedure as normal. Do you later in the course of the course give also examples, practical examples, how to do the follow-up procedure and classification, or how to connect in mid-level or high level? So that's not that straightforward, yeah?
In mid-level is rather straightforward, because at this point you consider this as alternative data, and you do classification on this data set concatenated. That's what you usually do with mid-level data fusion.
So the same way straightforward as in the first low level?
As in,
I don't see it at the moment, but must be correct.
I mean, these features are just new variables, so imagine, let me do like this.
No, but if
I
you
will
later in the course of the day or so give example, then it's not necessary to explain
I will show you also an example afterwards, but imagine this is one of your data set, and maybe the second data set is just, I don't know, pH, temperature, humidity. So in this case, you do principal component analysis, and then here you may have scope 1, scope 2, scope 3. Here, since you have only variable, you may decide to keep them as they are. And you consider that this is a new data set. Then, of course, you have to decide scaling. In this case, the most web sensible will be probably autoscaling. You may also decide that you want to this part to contribute to the model as this part, and this is called block scaling. We will see an example of this. So you may do simply this, you may do this plus this. You, as any time you decide something about preprocessing, and then you do classification. So for instance, you do linear discriminant analysis if you think that this is sensible, or PLSDA, or class modeling, whatever. And of course, imagine that you have a discriminant analysis. So maybe here you have your discriminant factor 1 and your discriminant factor 2, and you see very nicely the two classes. And then you want to know which is the contribution. Then maybe you look at the coefficient of your discriminant vector, and you see that this is very high positive, this is not important, this is negative, this is very important, positive, this is positive again, very important, this is negative. So your interpretation here is easy, because say, okay, pH should be high, temperature should be high, water should be low. In this case, you say, first principal component should be high. So what you can do, you can look the loading of your first component, and maybe this loading are like this. So I say, okay, this spectral region and this spectral region are important. So mid-level is, according to me, not so complicated to handle. And if you do regression, it's the same.
And you have to fully clear. You have to scale according to a variability, to uncertainty, and also to the dynamics of the data, as in the
yes,
level 1.
Exactly. As any time, when you think of a new methodology, you think that Your problem will be which method should I use? But then you realize that your problem is always the same problem. Which scaling should I use? Which is the most sensible preprocessing? It's always like that, because these are the most important steps, no matter the method you are using. Because, for instance, here, if you do autoscaling, what you do? You want that every variable count the same. So you are giving the same importance to all the variables. Now, in this case, we have 3 variables here and 3 variables here. Doing autoscaling are also giving the same importance to the two different methodology, because I'm giving the same importance to spectroscopy and the same importance to, let's say, ambient variables. But imagine that here I have the output of 100 sensors, because I am in a process, so I don't have a single temperature. I have maybe 50 temperatures, because they are thermocoupled in different height of my reactor or in different point of my line. And I have a flow in different position, and so on and so on and so on. So if this becomes 50 variables, and these are only 3 components, if I do the analysis with autoscaling, these will a bit disappear, because they are only 3. Okay? So I may think to scale, like this 50 will count as much as this 3. But this does not necessarily mean that I have put equal importance, because now, being this 50 and being this 3, if I want that this block count 1 and this block count 1, I have downsized a lot this part, and I have upweight a lot these 3 components. So the result will not really be a balance, will be this being more important. So even if usually when we teach, we say, oh, you should do block scaling, 2 equal block variants, and this is the way to do. Yes, this is the way to do if I'm only interested in the kind of block. But if I'm interested in classifying at best my sample, this is not always the best option. I have a small example of that in the application there.
We're going to do a feedback loop by these squares, right?
Yeah, yes. So what you can do is maybe to use an intermediate situation modulating your weights. I mean, this is always possible, that you tune the scaling in some way. And it's even possible that you do the analysis in both ways. You do autoscaling, then you do block scaling, then you see the result. You see the differences, and the basis of your knowledge of the system and the problem, you decide what is better. Or maybe you decide to have a larger model, one with one preprocessing and one with another one, and you do your final model on both of them. This is also a way of using data.
I'm not sure if I exactly follow, but in this case, are you saying that we would like do some sort of data reduction and then do the pre-processing before fusing the data?
Yes, in this case, if this is your question, you use the preprocessing 2 times, because you use the preprocessing here.
Right, before you do the data reduction.
Before the data reduction, because maybe you want to preprocess the spectra, you want to get rid of scattering or other effect.
Okay.
And then you do the preprocessing here. Because we want this fusion of the block in a sensible way. In this example, at this point, I decide to do none as preprocessing on this block. But of course, if this, imagine instead of this was, I don't know, chromatography, then I should do pre-processing here, because maybe I have shift in the retention times dimension. Maybe I have to normalize because I didn't weight exactly my sample. I want to get rid of this and so on. So yes, you need 2 pre-processing steps. And now I have a question for you. The fact that I have 2 pre-processing steps, what affect? Now we are building the model. Imagine we want to use this model on new data.
We make 2 transformations before.
Yeah, so this means that when I have new data, I have to store this pre-processing, I have to store this pre-processing, and I have to apply what I store. So for instance, I have to store the mean and the standard deviation if I do auto-scaling, and I have to apply this to my new sample. So, of course, in this respect, I have a complication when I do this compression, because I have to do something before data compression, and I have to do something after data compression, and I have to remember that I have to apply the pre-processing before, so I have to store it. We will come back to this also later on. Other question? Okay, so this is something which seems probably complicated, but I just try to explain you, because now we have talked about the 3 main approach: low level, mid level, and high level. But there is also I want to focus. I mean, there is nothing new in this, but I want to focus your attention at which level the fusion happens. So, if we do low-level data fusion, you follow the solid line. So with low-level data fusion, you have your different data set. I have called them X1, first data set, X2, second, XB is the last block you have, okay? So in this case, what we do is decoupling of the data augmentation, okay? And then we do the modeling. So the fusion, in this case, happens at the raw data. So when I speak about low level, this means I fuse, so the fusion step is in the raw data. My raw data or my block collector. When I do feature extraction or data compression, as we were talking before, the fusion is not at the raw data, because before I extract the feature, so the fusion is at the feature level. I don't fuse my raw data, I fuse the feature. So I fuse the feature and then I do the modeling step. When I do the high level, I may have both paths, because I can do the modeling in my raw data, each block separate distinctly, and then I take the decision, and then I fuse the decision, and this will be my final output. But I can also think of passing there, taking decision on there, fusing the decision here, and then the model up down. So what I'm telling you is that I have these 3 main approaches, but these 3 approaches can also merge. So what is important for you is that before you start doing something, it's like when you do experimental design, no? You first sit with a pencil and a piece of paper, and you write down, so what factor I want, how many conditions I want to study, which is the best way to do, and here is the same. How many single data sets I have, which are the shared mode, so do I have the same sample, so I'm sharing the sample. What I'm going to do, I'm going to extract feature or not, how I want to combine this, and with respect to the data fusion, the important thing is at which step I want to do the fusion, and at which step I will do my final model.
Is it possible to take to merge, for example, the raw data, features, and decision?
Of course, yes.
Wow.
The only thing is a bit like before. Anytime you merge things that comes from different steps, remember that you have to, what happened, always ask yourself, when I'm going to use my model for future samples, because I want to predict them or simply to project them in my model, what I will need, so it is feasible for me to store this information and to do this step, because this also can, let's say, help you to take a decision, because in principle what you suggest is possible. Then you start thinking, okay, I want something that functions in real time. If I have to maintain, let's say, 4 regression models for this high-level decision with their parameters, this means that I have to do the maintenance. Imagine a calibration, no? Most of you, I think, are familiar, because most of you works with spectroscopy, with the calibration. And you know that you have a calibration model now with spectra, and maybe in 2 months you have to do calibration transfer or update or so on. So imagine you have high-level data fusion, so maybe you have a 4 calibration model, you have to do the maintenance of 4 calibration model in the future. So ask yourself, will this be feasible in my application context or not? Because, of course, when we set up the model, we can spend time, invest money, and so on. But then we have 2 things. When we are going to use this model, how much it will cost me in times, in effort, do I have this? Is this really what I want? That's because we can always improve our modeling. We can always improve our classification or our prediction. I can always improve the time from Bilbao to here. If I buy a nice Ferrari, but can I feed my Ferrari with my salary? Maybe not. So that's I mean the kind of consideration.
I have one question. In the case of the low level, comparing the low level and the high level, for instance, in the low level, you mix the raw data. For instance, I am working with near infrared and with the Raman spectroscopy. I try to fuse the matrix from me and matrix from Raman. But then I have to do a pre-processing. But maybe the pre-processing of the near spectra is not the best pre-processing for the Raman spectra. And you don't know which is the best pre-processing up to obtain the models. So you are generating a lot of models, and then to choose which the pre-processing is the best one. So in this case, it would be better to use a high level, I mean to combine the different models, or to try to choose the best pre-processing, and then when you have to choose the best pre-processing, try to use the low-level techniques.
But in this case, the work is the same. Because in any case, you will have to choose the best preprocessing for the two separate data sets. And when you fuse them, you do not need the preprocessing to be the same. Can be different. I mean, you can do baseline correction for Raman and take care of the fluorescence with some specific methodology. And you can do, I don't know, SMB for the near infrared. So you do not need the preprocessing to be the same. You preprocess them in a distinct way, and then what you merge are the preprocessed spectra. If you have to do the high level, you have to do the same, because you have first to preprocess your Raman spectra, first to preprocess your near infrared spectra, and then you build your model. So basically, what you do is not so different, according to me, in this case.
Also,
Because I disagree.
no, I completely agree. No, I was adding a little bit more that there is something called ROSA. Are you going to talk about ROSA?
Yeah, yes, I have a sample.
Okay, so then I will not say anything. Because ROSA is merging many different preprocessings to
Yeah.
get the best out of each preprocessing for the same data set.
Then I want to mention you this, also because we will see one method based on this idea. This maybe for some of you is a bad word, kernels. I don't know, someone may be familiar, someone not. But to keep it very simple, sometimes just think of a single data set. Sometimes you have situation in which you don't have you don't want to really use the raw data. Because maybe your sample are very overlapped in the raw data, and maybe you want to have a better separation somehow. So if you want to distinguish these two, in this situation is maybe not so easy. So sometimes what you do is that you do some transformation that focus more on the sample similarity.